Hello everyone. In this segment, I'm going to demonstrate how to use vGray 5S to determine the Plume function of your source, be it an evaporation source or a sputtering source. First, I would like to clarify what a Plume function is. A Plume function describes the vapor cloud originated from a single point of a source. More precisely, it is the distribution of the flux density as a function of the polar angle. The overall flux, which is responsible for thin film deposition, is a summation of flux emitted from the entire source surface. In the simplest case, when we treat an evaporation source as a single point source, then the overall flux is simply determined by the Plume function itself. I should mention that PVD modeling is often carried out without precise knowledge of the Plume function. In many cases, you can make a guess, or you can look it up from literature. That said, not knowing the Plume function well of your particular source is a hindrance to achieving the best results of your coating jobs. With this in mind, I will use two examples to demonstrate how to use vGray 5S to determine the Plume function. This first experiment is to determine the Plume function of a planar magnetron sputtering source in a rather simple experiment. And I would like to mention that in order to determine the Plume function of any source, you obviously need to conduct some experiment and to measure a distribution of thickness over a certain distance and record all the measured data. And you have to um, enter all this information into the software in order for the software to determine what the Plume function is. And so let me load this first example. Uh, Now, this is a rather common experimental setup, and we have a magnetron sputtering source, and that's facing a substrate holder that's normally rotating. But in this case, for the purpose of determining the Plume function, the substrate is held uh, constant and not moving. And this shows the erosion track of this magnetron source. Now we have conducted measurement and many data points, sampling points have been measured and stored in a data file which we can import. Let me now go to the Fit Plume panel. That's where you can import the measured data. We click here. Now this is the measured data. So we have 31 measured thickness along the diameter of this substrate holder. And the first thing you do now here is after you load the experimental data is to make a guess what the Plume function is. It doesn't matter whether you know it or not. You just you can just test it. Gives something. Here we can assume that the Plume function is a pure cosine, which is actually realistic for some evaporation. In sputtering case, it's more rare to see a pure cosine. But for the sake of using the software, let's assume that's the case. Now let's compute with that guess and see whether they agree with one another. The red line is the thickness distribution by this guessed Plume function, a pure cosine, and we can see that it does not agree well with the experimental data, which are these green uh, points. So at this point, you can change your guess Plume function. Let me change one of the number. So we sort of compress the cosine from the middle, make that fatter. And in this case, this could be more realistic for a sputtering source. And we make another computation. Now we see these two curves agree a little better with one another. So at this point, you can make a further guess, or you can engage a automatic plume fitting routine, which is built in the VGray 5S. And before you do that, you wanted to determine how many terms in the plume function you want to fit. In a vast majority of physical vapor source, you only need two cosine terms in this three cosine term expression built in this software. So if we just want to fit the two term, you don't use these two numbers, and you only need to fit these three numbers. In fact, to describe a two-term cosine Plume function, and you need a full quantity, but the first one can always be one, so you only need to determine the three. So we select these three quantities to fit, and all you need to do at this point is just to hit fit. All right, the fitting has completed. We can see now the blue curve here is the result of a new Plume function that's determined by the routine of the software. And we see that that fits very well with the experimental results. And how much improvement we have here can be also seen through the squared error. For the guessed Plume function, the squared error is this quantity. Now with the um, automatic fitted Plume function, we have a square error, which is one order of magnitude smaller. So I would say this is a pretty good result. And this blue diagram here is the Plume function of your source. This kind of a distribution is actually quite common. Um, that probably is a target that's been used for some period. And if we like the results, and you can hit this adopt button, and then your new Plume gets transferred to the source panel. Now you have this exact Plume which you just obtained, And from that point on, you have very good knowledge of your vapor plume function, and that will allow you to conduct further modeling work, and will give you good results compared to just having a gas plume function. We will now proceed to the second example. So this one is slightly more complicated than the first one in the sense that the deposition was carried out while the substrate holder is rotating. Let me load this experiment. So here it is. And in this case, we have again, a planar magnetron source, which has a erosion track like this. It's a circular magnetron, which is very common. And then it's arranged in such a way that the substrate holder, and here's the magnetron that's facing the substrate holder with the tilt angle. And here's the 3D representation of the experimental setup. Now we will attempt to determine what the Plume function is for this particular source. So let's go to the fit Plume panel. Again, we can load the experimental data. That's this file. So in this case, we measured 10 sampling points along a radius of the substrate holder, 10 points. So these are the experimentally measured points. And so the first thing we do here again is to simply make a guess what the Plume function is. And so let's just use this what's already entered here. It doesn't really matter what guess you use, and we compute. So now we have this red curve. That is the result of the thickness distribution according to this particular Plume function, which have these parameters. So apparently, the guessed Plume function does not produce the type of thickness distribution which we observed in the experiment. So, and at this point, you can change these values to manually fit the experimental data, or we can do the same thing as the last example. We just hit the fit. Then the automated routine will be looking for the Plume function, these parameters that gives the best fit of the calculate value. So it will take something like 30 or 40 seconds, depending on how much computation is involved. Okay, now we have a new curve, the blue one, which is computed based on this new Plume function. At the center of that is very compressed and very different from our guess. And in fact, this type of Plume function is quite common for magnetron sputtering targets. Sometimes it's more common in targets that's very flat, very newly polished. And so in any case, this seemed to fit the experimental data very well. So in this case, we can again hit adopt, and then these values will be uh, transported to the source panel. Now you have a vapor plume function, looks like this, and essentially you have calibrated your source, and from that point on, you can change your configuration and do things uh, to make your deposition process better. I would like to spend a couple more minutes to show that now we have a good knowledge of the source Plume function, what we can do. So now we have a Plume function that looks like this as a result of the Plume fitting we have just done. And let's first calculate what kind of a thickness distribution we will have. So let me turn off the last computation. So this is the thickness distribution we will have on the substrate holder, and from the center of the substrate holder to the edge, we have a distribution that looks like this. The non-uniformity is plus minus 8%, which is not great. And so the question is what we can do to improve thickness uniformity. And one of the things we can try is to change the geometric arrangement of this deposition process. And the first thing I would like to try is to increase this distance. That's the distance between the center of the substrate holder and the source, the sputtering target. So here's this distance D. I will change that from 2.25 to 3 inches. Okay, now I will calculate. So now let me see, 2 curve. So this blue curve is the result of the last computation. That's before we change the distance. So this new distribution is much more uniform, and it has a non-uniformity of plus minus 2.2%, which is much better. And so clearly we can further adjust this distance and that distance, and also maybe the tilt angle to find a much better thickness uniformity. And I have done several trials and found a pretty good configuration, which I saved. Now I'm going to open. So this is the optimized, in one way, optimized uh, physical arrangement of the deposition process. And so I increased this distance and increase that vertical distance as well. And also I increased the tilt angle of the substrate of the source by 5 degrees. Now let's recalculate. So again, this red curve is the current result, which indicates that in this new configuration, we have a thickness uniformity. The non-uniformity is plus minus 0.5%. So that's again a very substantial improvement in the thickness uniformity. So this is a pretty good result. And so the old results, if we remember, that's plus minus 2%, which is an improvement from the original configuration that gives plus minus 8%. So we can, with a good knowledge of the source Plume function, we can discover um, geometric arrangement that gave us much better thickness uniformity. So you may ask what we have to sacrifice in order to obtain a good thickness uniformity. One thing you will uh, have to accept is that having this more uniform thickness distribution, your deposition rate will be lower. How much lower you can actually discover by computing the material collection. You just check this box here and you do the same computation. So this number here, material collection, is the percentage of material vapor collected by your substrate holder. So this good thickness uniformity arrangement, you collect only about 15% of the vapor. The rest of the material vapor just escapes the substrate holder, gets deposited on the chamber wall or being pumped away. So this is not a good collection efficiency. However, it is not uncommon. I know many labs, they have arrangement in not for them to get good thickness uniformity. They actually do have a process that have quite low collection efficiency. So this is a low collection efficiency means low deposition rate. Uh, Consider that if you have the same power sent to your target, and if you have a low collection efficiency, that means the deposition rate is low. In this case, actually, compared to the original case, which has 8% plus minus 8% of thickness uniformity, that has a deposition rate about 40% higher. So you sacrifice 40% of the deposition rate to get a much, much better thickness uniformity. Of course, this kind of optimization is not the only way to achieve thickness uniformity. You can use other techniques to obtain good thickness uniformity, also have good material collection, meaning high deposition rate. I will wrap up the session here. I hope this tutorial has been helpful. You may want to leave a comment here or contact us and let us know what subject you would like us to cover in our next installment. Thank you, and please stay in touch.